Hello everyone. Today, we re-venturing into the most extreme mind-shattering corners of the cosmos to explore the single heaviest type of object known to science: celestial bodies, so impossibly dense that a single teaspoon of their core material outweighs an entire mountain range here on Earth. We often think of heavy things in our daily lives: skyscrapers, ocean liners, mountain ranges. But all of these fade into irrelevance when we face the true champions of cosmic mass: neutron stars. These are not just stars. They are the compressed, ultra-dense cores of massive stars that have died in the most violent explosions the universe has ever seen, supernovae. To understand their absurd density, we first need to rethink what weight and mass mean on a cosmic scale. On Earth, the densest natural element is osmium, at just 22.6 grams per cubic centimeter. A teaspoon of osmium is heavy, but it is still something you can hold in your hand. A neutron star, its density hits approximately 10 to the power of 17 kilograms per cubic meter, equal to the density of an atomic nucleus itself. Let that sink in. A single teaspoon of neutron star material weighs roughly 10 billion tons, equivalent to the mass of a large mountain, or even the entire weight of Mount Everest, compressed into a tiny spoonful. If we could somehow bring that teaspoon to Earth, it would cut through the planet's crust like a knife through butter, falling straight toward the core, unstopped by any material we know. This level of compression is not just impressive. It redefines the limits of matter and gravity. Let's rewind the clock to understand how these cosmic giants are born. Neutron stars form from stars that start their lives with 8 to 20 times the mass of our Sun. For millions or even billions of years, these stars burn brightly, fusing hydrogen into helium, helium into carbon, and so on until their cores forge iron. Iron is the dead end of stellar fusion. It cannot release energy through fusion, so the star's core suddenly loses the outward pressure that balanced gravity for eons. In the fraction of a second, the outer layers of the star crash inward at 15% the speed of light, slamming into the inert iron core with unimaginable force. This catastrophic collapse triggers a supernova, an explosion so bright it can outshine an entire galaxy for weeks. The outer layers are blasted into space, seeding the universe with heavy elements like gold and platinum. But the core, it is squeezed so violently that electrons are crushed into protons, forming pure neutrons. Every atom is dismantled, and all empty space within matter is erased. What's left is a sphere roughly 10 to 20 kilometers across, smaller than many cities, but holding 1.4 to 2 times the entire mass of our Sun. Imagine squeezing the mass of 2 suns into a ball the size of Chicago. That's a neutron star. The story of how we discovered these extreme objects is one of the most thrilling tales in modern astronomy. For decades, neutron stars existed only in theory. In the 1930s, physicists Baade and Zwicky proposed that supernovae could leave behind ultra-dense neutron cores, but no one had ever seen one. That changed in 1967, when a 24-year-old graduate student named Jocelyn Bell was working with a radio telescope at Cambridge University. She noticed strange, perfectly regular radio pulses repeating every 1.33 seconds, so precise that her team initially thought they might be signals from an alien civilization, nicknaming the source LGM-1, short for Little Green Men. Soon, more pulsating signals were found, and scientists realized they were observing rapidly spinning neutron stars, now called pulsars. These stars act like cosmic lighthouses, shooting narrow beams of radiation into space as they spin hundreds of times per second. Bell's discovery revolutionized astrophysics and proved that neutron stars were more than just math. They were real extreme objects scattered across the cosmos. Today, NASA leads the charge in studying these mysterious giants using cutting-edge space telescopes. The Chandra X-ray Observatory peers into the high-energy X-ray light emitted by neutron stars, mapping their surfaces, magnetic fields, and gravitational effects. The James Webb Space Telescope recently captured groundbreaking evidence of a young neutron star at the heart of the SNEN 1987, a supernova remnant, giving us our first clear look at a newborn neutron star. What these missions reveal is nothing short of astonishing. A neutron star's surface gravity is 200 billion times stronger than Earth's. If you stood on its surface, something you could never survive, as gravity would instantly flatten you into a thin layer of atomic matter. You would weigh more than all of humanity combined. Its magnetic field is trillions of times more powerful than Earth's, warping the paths of light and particles in ways that test Einstein's general relativity to its limits. Some neutron stars spin so fast that they complete a full rotation in just over a millisecond, faster than a blender blade, faster than any man-made machine. What keeps a neutron star from collapsing further into a black hole? It has a quantum rule called neutron degeneracy pressure, a law of physics that says number 2 neutrons can occupy the same space at the same time. This quantum force is the only thing fighting against the crushing gravity of the star's mass. If the core were just a bit more massive, over 3 times the sun's mass, even this quantum barrier would break, and the star would collapse into a black hole, the only object denser than a neutron star. This makes neutron stars a perfect cosmic middle ground. They are the last stop before matter vanishes into the infinite density of a black hole, letting us study the edge of known physics without crossing into the complete unknown. Beyond their raw numbers, neutron stars matter because they unlock some of the universe's deepest secrets. They are laboratories for physics we cannot replicate on Earth, teaching us about gravity, nuclear physics, and the behavior of matter at its most extreme. They are also the source of heavy elements that make life possible: gold, uranium, platinum, all forged in the supernova blast that creates a neutron star, and scattered across space to become part of planets, asteroids, and eventually living things. When you wear a gold ring, you're re-wearing material forged in the same catastrophic explosion that births a neutron star. These objects are not just distant curiosities. They are part of our cosmic ancestry, connecting us to the violent, beautiful life cycle of stars. Standing back and thinking about neutron stars fills us with a kind of awe that defines space exploration. We look up at a night sky full of stars, not realizing that some of the faintest, most mysterious points of light are the densest, heaviest objects in existence. They remind us that the universe is not just big and empty, it's full of extremes that stretch our imagination to the breaking point. A spoonful of material that weighs as much as a mountain is more than a fun fact. It has proof that the universe is far wilder, more powerful, and more wonderful than we can ever fully grasp. Every time we study a neutron star, we push the boundaries of human knowledge, taking another step toward understanding the rules that govern everything from atoms to galaxies. As we wrap up this journey into the heart of cosmic density, remember that the universe is full of these mind-bending secrets waiting to be uncovered. Neutron stars are just one example of how space continues to surprise and humble us, turning impossible ideas into observable reality. They challenge us to think bigger, dig deeper, and keep looking up at the stars with curiosity and wonder. Please like, comment, share, and subscribe to the channel